Hello, I'm Ryan Baker, and this is Big Data Education. Today we're going to continue our discussion of the k-means clustering algorithm by discussing how we validate a clustering scheme and choosing a selection of k. So how do we choose a value of k? And for that matter, how do we choose which set of clusters to use after we've done 17 randomized restarts? Let's start with the simpler case, where we have 17 randomized restarts. Could be 4, could be 9,075, and each of those randomized restarts involves the same k, the same number of clusters. So the metric that's often used to select which scheme is the best, which set of clusters is the best, is called distortion, which is also called the mean squared deviation. With distortion, we take each point P, and we find the centroid of P's cluster C. And then we're going to take that distance d from C to P. So how far is each point from its centroid? We're going to square all those distances to get d prime, and sum all those d primes to get the distortion. You may say, okay, Ryan, you said we're going to take the distance between the 2 points, but how do we get that distance? There's a lot of distance functions you could use. You could use Manhattan distance. Typically what people do is use Euclidean distance. Euclidean distance is just the standard thing you learned in geometry class in high school or junior high or college, whenever you took it. And it's the distance from A to B in 2 dimensions is shown as such. You take each point and you take the distance from that point to the centroid on each dimension, and you square each, then you add all those squares together, and then you take the square root of the whole thing. And that generalizes. You can compute Euclidean distance for an arbitrary number of dimensions, and all it is the distance between the point and the centroid on each of the dimensions, squared and added together, and then square rooted. The distortion works for choosing between randomized restarts. It doesn't actually work for choosing cluster size. And why is that? Because more clusters almost always leads to smaller distortion. When you have more centers, there's going to be some center every point is probably closer to, unless they all end up in one place, in which case you don't really have more centers anyways. So the distance to the nearest cluster center should almost always be smaller with more clusters. And it only isn't when you have bad luck in your randomization and all the centroids end up piled up together. Aha! I'll use cross-validation, I hear you cry wherever you are. Well, it's a good idea usually, but cross-validation actually can't solve this problem. It's a different problem than prediction modeling. You're not trying to predict specific values, you're determining whether any center is close to a given point. More clusters are going to cover the space more thoroughly. So distortion will often be smaller with more clusters, even if you cross-validate. Let me give an example. Let's say that you have 14 centers, ill-chosen, and you might get this by conducting cross-validation with too many centers. By contrast, let's take 2 centers which are very well chosen, and you might get this by conducting cross-validation with not enough centers. Here's the 14-point case, and you can see the centroids have nothing to do with the data points, really. And here's the 2 centroids, and you can see in this case, there's kind of 2 major groupings, and this one is kind of capturing both of them. There's one on the left, one on the right. There's really not enough points here, not enough centroids to capture these points and the way they cluster, but this is probably about as good as you can do. So in fact, those ill-chosen 14 centers are going to achieve a better distortion than the well-chosen 2 centers. Because even though the 14 centers had nothing really to do with the actual points, they're still kind of closer and they fill the space better. So the solution is, rather than using cross-validation, penalize models with more clusters according to how much extra fit you'd expect from the additional clusters. And you can use the Bayesian information criterion or the Akake information criterion from week 2 to do this. It's not the same as cross-validation for this problem because of what we just talked about. So how exactly do you use an information criterion for this? Well, first you assess how much fit would be spuriously expected from a random n centroids without allowing the centroids to move. And then you assess how much fit you actually had. And then you find the difference. So the question is, how much more fit did you get than you'd expect just from having n random centroids, just randomly distributed? And then you can say, how many clusters? What you do is you try several values of k, and you find the best fitting set of clusters for each value of k, typically using randomized restart, and then you choose the k with the best value of BIC or AIC.
Another way of determining how many clusters to use is silhouette analysis. In silhouette analysis, a silhouette plot shows how close each point in a cluster is to points in adjacent clusters. Silhouette values, like our old friends Ko and Kappa, are scaled from -1 to 1. If they're close up to +1, then the data point's far from any of the adjacent clusters. If it's close to 0, it's the boundary between clusters. And if it's close to -1, the data point's closer to the other cluster than its own cluster. So for each data point I, we take the average distance of that data point I from all the other data points in the same cluster C. We then find C star, which is the cluster, the lowest average distance of I from all other data points in cluster C star. So in other words, aside from a point's own cluster, what cluster is closest to it? That's C star. And then we take the average distance of I from all the data points in that cluster, C star. And we're basically going to say, how much closer is a data point to its own cluster than to another cluster? And again, if a data point is closer to another cluster than its own cluster, you got a problem. The example I'm about to show you comes from this web page. So here are a couple of good clusters. You can see on the graph on the left, each data point, the x-axis represents how good the value for that data point is. All the green ones, that's the first cluster, what their goodness is, and all the black points, that's the second cluster, what their goodness is. And you can see here on the right that in fact the green and black clusters are pretty good. Green's way over up on the top right, black is kind of down the bottom left, and we have points that in general have a good silhouette value. The vertical line on the left is actually the average silhouette value. What if we have 4 clusters? It's still pretty good. We now have a yellow, black, and green, and a blue. You can imagine, you can see blue is the best on the left. That's because blue is pretty far from everything else. Black, yellow, and green have some data points that are kind of worse, that are kind of on the fringes. But still, you can see a relatively plausible clustering, and you get a good average silhouette value, the vertical line. Here's a bad clustering. We now have 3 clusters, yellow, blue, and black. Well, blue's pretty good, but black has a lot of those data points that are in the middle between the 2 black kind of subclusters that end up being very close to yellow-green. So as a result, we have a bad clustering here, and we have a relatively bad average value, the vertical line. Here's another bad clustering. In this case, we've actually split that bottom cluster into 2, and you can see on the left, orange and I guess that's teal, do quite poorly. They have a lot of points that are very close to the other cluster. And so as a result, we get a bad average value. And finally, if we split it even further, we do worse still. So in this example, this last one, the clusters 2 and 4 are reasonable choices, but 3, 5, and 6 are not good choices. An alternate approach is to use the eigengap. This only applies to spectral clustering, which we haven't talked about yet, so I'm a bit out of order here. But in spectral clustering, you also have the option of choosing the number of clusters that maximizes the eigengap, which is the difference between consecutive eigenvalues, which is how you represent your clusters. Finally, one last alternate approach is to ask when you're choosing the number of clusters, why am I conducting cluster analysis in the first place? If your goal is just to discover qualitatively interesting patterns in the data, you may want to do something simpler than using an information criterion or a silhouette analysis. You might just want to add clusters until you don't get interesting new clusters anymore.
In the next lecture, we're going to talk about advanced clustering algorithms. I'm Ryan Baker. This is Big Data in Education. Thank you very much. Have a good day.